This is my second report. The current report explores delamination in a multi-layer beam-like structural component under harmonic load applied in its midspan. The component explored is symmetrically delaminated by two delamination in its two ends. Besides, the component is placed on two springs. The delamination under harmonic load is explored by the integral J. The extreme values of the total J are estimated. The strain energy release rate is deduced from the energy balance in the conditions of harmonic load for checkup of the J integral. The extremals of the total strain energy release rate confirms the maximum and minimum of the total J integral. The evolution of the total J with spring constant, static, and harmonic load is qualified. The geometry of the beam-like structural component studied in the current paper is reported in figure number 1. The structural component is subjected to a harmonic load F. The maximum value of the load is Fq. The harmonic load is generated by a motor of mass mp. The motor weight P is given by formula number 1. The beam-like structural component is symmetrically delaminated by two delaminations as shown in figure number 1. Because of symmetrical character of the delamination, only part H3, H4, H5 of the component is treated in this analysis by applying the J integral. The total volume for both delaminations of the J integral under static load can be estimated by using formula number 2. Equation number 3 estimates J as a function of P. Here, D1, D2, and D3 are parts of the path of integration D. The values of J are found by applying equations number 4, 5, and 6. Equation number 7 defines the specific strain energy density. The curvature and the coordinate of neutral axis are determined from the longitudinal force and the bending moment by applying equations number 10 and 11. Equation number 14 is used to define the variation of the modulus of elasticity transversally to the layer. The quantities involved in equations number 5 and 6 are determined by an approach similar to that defined by equations from number 7 to number 11. The total value of the J integral under load Fq is estimated by applying equation number 17. Here, J is a function of Fq and is determined by using equations from number 7 to number 13 after a replacement of P with Fq. Equation number 18 is used for determining of J dn under harmonic load. Here, n is the number of revolutions per of the motor per minute. Delta is the displacement of point H3 induced by the motor weight. Equation number 22 is used for delta. This equation is written by applying the integrals of Maxwell-Morse. Here, Ki is the curvature, Mi is the bending moment from the virtual loading. C is the spring constant. The beam is supported by two springs as shown in figure number 1. The total volume of the J integral is obtained by applying equation number 23. In fact, equation number 23 estimates J maximum. The minimum J is estimated by applying equation number 24. The strain energy release rate under harmonic load is deduced from the energy balance for checkup of the J integral solution. Equation 25 gives the strain energy release rate induced by the static load P. The energy balance results in equation number 26. Here, B is the beam width, U is the strain energy. Equation 27 can be used to estimate U, the strain energy. Here, specific strain energies are determined by applying equations number 29 and 28 and 29. The strain energy release rate induced by the load F2 is found by applying equation number 33. Here, G is a function of F2 and is estimated by applying equations number 26 and 27 after replacement of P with FQ. The strain energy release rate induced by harmonic load is obtained by applying equation number 34. Equations 35 and 36 can be applied for estimation of maximum and minimum of the total strain energy release rate. The extremals of the total strain energy release rate induced by harmonic load confirms the maximum and minimum of the total volume of the J integral, which is a verification of the solution. The results reported here concern different aspects of delamination in beam-like structural components under harmonic loads. To qualify the change of the maximum J with N, the J maximum N relation is reported in figure number 2. Figure number 2. The curve in figure number 2 highlights a strong nonlinear relation between J maximum and N. The most important feature of the evolution of J maximum with N is that J maximum grows with a rapidly increasing rate, as can be seen in figure number 2. To shed light on the correlation between J maximum and C, the J maximum C relation is shown in figure number 3. This relation is also strongly nonlinear. A significant reduction of J maximum is seen in figure number 3. The rate of the reduction, however, decreases. Next, the investigation is focused on the evolution of the maximum J with varying the mass MP. The relation between J max and MP is reported in form of a graph in figure number 4. Figure number 4. The first that captures the attention is the nonlinearity of the J-max MP relation. Another interesting observation is that J maximum grows at a rising rate. The evolution of the maximum J with varying of FQ is also a subject of exploration in the current article. This exploration results in the J max FQ relation, whose graphic is reported in figure number 5. Number 5. The relation is nonlinear. Besides, it can be seen that J max has a growing rate.